One of the problems with our Tetris game as it stands right now is that when you're up against a wall like I am right now, you can't rotate the piece. So if I press the up arrow, I can rotate it there, but if I get closer to the wall, now I'm mashing the up arrow key and it just won't rotate. Now this is a good thing. It means that our code is working correctly, because if we did rotate the piece right now, a small part of it would be outside of the grid. This piece, this sort of center piece right here would stay in place, these two would rotate down, but then this little piece on the bottom would end up to the left outside of the grid. And we have some code in place here that says when we press the up arrow, when we go to rotate, first check if the piece is valid. Check if after you rotate, will it still be a valid piece that's totally on the board. And only if it's valid do we then update the piece's rotation. So this is a good thing. It's better than allowing invalid pieces. But as a player, it sometimes feels wrong. It feels like, well, this is a bad example because the yellow piece doesn't rotate. But if I'm here trying to rotate my piece, pressing the up arrow, it feels like it should just work. And what happens in real Tetris is something called a wall kick, where if the piece needs to move away from the wall, again, I'm pressing the up arrow right now, on the right wall as well, it won't allow me to rotate. If a piece is up against a wall like that, it will try to kick the piece out. So when I press the up arrow to rotate, it will rotate the piece and also move it to the side automatically. I can do it manually. I can say, look, it won't let me rotate, so I'll move to the right and then rotate. But what would be really nice is if just pressing the up arrow would cause that to happen automatically. And so what we want to do in this video is implement wall kicks, the same way that Tetris has them, so that rotating the piece is a little bit smoother. Now, on this Tetris wiki, I have found sort of a specification that details exactly how wall kicks are supposed to work. So these two tables show how the game tries to kick the piece out. So it's different for the I piece, that's the really long one, versus all of the others. But essentially what these 5 columns of the table are 5 different places that we can try to put the piece to see if it works. So you can see that all of them start with 0, 0, and these are x and y coordinates. So you start at x of 0, y of 0. And these are not actual points, they're sort of the change in the position. So what we're saying is the first thing you should try when you rotate a piece is using 0, 0, is not moving it, not kicking the piece at all. Just try rotating it in place right where it is. And if that works, then great, you've rotated the piece, there's no problem. In most cases, that's what'll happen. But imagine that there is a problem, that when you rotate this, the piece is not valid, and our if statement doesn't run. Then, rather than just refusing to rotate the piece, we should move on to test number 2, to this second column. And in test number 2, you can see we have some x and y coordinates. In this case, it's always the x coordinate that changes. So when we have -1, 0, this is an x of -1. And so what we're saying is, you should try shifting the piece 1 x position to the left. And see, when you shift it left, now is it valid? If you rotate and shift 1 to the left and leave the y alone, if it's valid, do that. Use that move. Use that kick in order to make the piece valid and allow the rotation. If that doesn't work, if you move it left and it's still invalid, then you try test number 3, which is to move left and down, a +1 here. Actually, I think it's up, because this Tetris wiki has positive y values going up, where in our game, positive y values mean bigger list items. It's going down. But essentially, they're saying move 1 left and 1 up, and try that. And if that works, great. If not, move on to this, where we stay at the same x position, but move down by 2. See if that kick works. If not, move to number 5, where we move 1 left and 2 down. And so you can see there are all of these different sort of kicks that you try, all of these different ways that you might try to move the piece in order to make the rotation succeed. But of course, I've just been looking at this first row. There are actually lots of different rows here, and each row represents one type of rotation. So you can see we have 0 to 1, and then 1 to 0, 1 to 2, and all of these are representing different start and end rotations. So in our variable, we have this, or in our project, we have this variable called piece rotation that goes from 0 to 3. And so 0 is sort of the standard rotation. Well, that's a bad piece to demo with. 0 is the standard rotation, and every time you go up by 1, you rotate the piece clockwise. So what this is saying is if you're doing a rotation and you're going from a rotation of 1 to a rotation of 2, so you started at 1 and you rotated clockwise, in that case, use this row, use these 5 tests to try to kick the piece out to the place where it belongs. And if any of these work in order, as soon as you hit a test that works, then you sort of kick the piece there and allow the rotation to succeed. If none of them work, then we do the same thing that we already do, which is just prevent the rotation entirely. So we have all of these different sort of rows representing different types of rotations, and we have 2 different tables. One for most of the pieces, and then one for the eye piece, just because the eye piece is a little bit different and needs to be kicked in a different way. So this data I have sort of taken and put into a spreadsheet here. This is the same information. You can see we still have the 2 tables, one for the regular kick and one for the eye piece kicks. And what I've done is I've taken sort of the first column here that tells us where we start and how we rotate, and turned it into these 2 columns, the starting rotation and the direction of rotation. So rather than taking the start and the end, I just have the start and the direction that we're rotating. Then I've taken each of the X and Y pairs, these sort of points, and split them up into 2 columns where we have X and Y, X and Y, X and Y. And then the last thing that I've done is sort of color-coded each of these. So you have green for positive numbers, red for negative numbers, and then sort of the darker colors when it's a 2, and the paler colors when it's a 1, and white for 0. And all of this you can do in Google Sheets automatically using conditional formatting, which is kind of nice. So we have these 2 tables, and I've been trying to think, what's the best way to organize this information so that we can program it in our Scratch project? And my initial thought was that we'd maybe have a bunch of if statements. You could have lots of different if-else statements that are trying to determine which X and Y position you should try. We're trying to figure out which coordinates to kick to make the piece go where we need it to go. And so I was trying to look for a pattern in this data. How could we say, maybe make a custom block that says, given a starting rotation and a direction of rotation, how can we find the entire sort of row of kicks that we should try? And I was looking at this first one, and I reorganized the start and the direction and tried to make all these sort of look like there's a certain pattern to them. But the honest truth is that there's just not much of a pattern. The best pattern I could see was that there are always 2 types of rotations that sort of go together, where all of the kick tests are the same. But other than that, there's just not much of a pattern, and I was struggling to see how we could do a good job of programming this in code, especially when you get to the eyepiece table, which is even sort of more chaotic. This is the best I could do of organizing it sensibly, and it really looks just kind of like a mess. So I was kind of thinking, rather than trying to program an if statement, program some code that can sort of use logic to determine something fundamentally illogical. It feels like all of this data is sort of random, and to try to create logic, to try to create code that would determine, what these X and Y values are, just seemed like really kind of a pain, and I couldn't think of a good way to do it. And so what I decided is, rather than trying to create a logical system for determining illogical values, we're going to make a logical system for finding illogical values that are stored in Scratch lists. We'll just take all of this sort of seemingly random data, we'll store it in Scratch lists, and then we'll come up with a good system that allows us to find the correct list item that contains the data we need using a simple script. So I've taken all this information and I've reorganized it. And then down in this bottom tab here, there's a second tab to my spreadsheet. And this is all the same information, but organized in a different way. Now, if you want to check out this spreadsheet yourself, it will be available. I think there will be a link in the description of the video. Maybe I'll make a little eye pop up. You can do that right now on YouTube. But you'll find it somewhere. And you can check this out for yourself. But this right here is all the same data organized differently. So you can see that previously we had two tables, one for most pieces and one for the I piece. Now we just have one big list of x and y coordinates. This is sort of all of the different possible tests. But the I and non-I pieces, all that information belongs in column B now, where the first 40 rows in this list, the first 40 items, are all the non-I pieces, the regular pieces, and then the last 40 rows are the I pieces. And so these two tables have sort of become two different lists just joined together. Then the starting rotation, rather than being this first column here, is now represented in column C. We've got this start rotation that goes from 0 to 1 to 2 to 3, and then 0 to 1 to 2 to 3 again. And then we have the direction and the test number and everything. And you can see that this data, the sort of resulting x and y coordinates, the kick coordinates that we need to test, look really random. But that's okay, because we can just take these numbers and put them directly into a Scratch list. So that's all good. But the question is, if we have this and this in a list, how are we going to make... We'll have two separate lists, I should be clear. We'll have a kick x list and a kick y list. But the question is, if I know what piece type I have, I know my starting rotation, I know the direction of the rotation, and I know which test I want to look for, I still have to figure out which list item should I go to in order to find the x and the y that I should sort of kick towards. And we want to run all 5 tests each time that we do a rotation. And so we have to be able to find the correct list item. And this is really the challenge of what we're trying to code. Now, fortunately, the setup, the way that I've organized this list, is actually going to make it pretty simple. And just to prove to you that this is something that's totally doable with a computer, I've actually sort of implemented all of the code that we need in this spreadsheet. So I can type in a piece type. We'll go with a T piece, just to show that that's not an I piece, right? So this is going to be one of the not I rows rather than the I rows. We've got a T piece, not an I piece. I'm going to do a starting rotation of 1. So we know that we're going to be somewhere in here. You can see it's already highlighted a row. It's not quite right yet because I haven't filled in the last 2 pieces of information. But we know it's going to be somewhere from 12 to 21, these rows, or 11 to 20 based on this number here. Then we can enter a direction. So let's say that we're rotating clockwise to the right. We're rotating in direction 1. And you can see that we sort of narrow in on now 16 through 20 as the possibilities. Then we can choose a test number. Maybe we already did test 1, we already did test 2, and we want to try test number 3. And you can see that we have successfully found row 18. I'm not using the numbers built into the spreadsheet. I'm actually using sort of this number column here. Row number 18, or list item 18 in our Scratch project, this is the one that's going to give us what we need. It's going to give us the x and y coordinates that we should kick to. Because we have a piece type of T, that's not I, a starting rotation of 1, that's correct, a direction of 1, that's correct, and a test number of 3, that's correct. It's found the right row that has all the information that matches up to sort of our requirements. And so if we can make a custom block that essentially does this calculation, that says, given this information, I'm going to find the list item that you need to kick towards. If we can just write that script, then it's pretty easy to try all the different kicks, right? We know this information using our variables in our project, and then we can just go through all the tests, 1 through 5. And you'll end up with these list items that tell you all the different coordinates that you should try kicking towards. But of course, the question that remains is, how did we do this? How did we make the computer know which list item to look at? And it turns out that the process is actually pretty simple. The first thing that we can sort of identify is that rows 1 through 40 are all the non-I pieces, and then 41 through 80 are all the I pieces. And then within those 2 sections, it's maybe easier to see if I zoom out a little. Even if you can't read the individual numbers, the colors should help you see the pattern. Within the top half and the bottom half, everything else is the same. So the starting rotation, the direction, and the test number, it's blue on blue. It's maybe hard to see what I've highlighted here, but all of these sort of cells match exactly all of these cells. So sort of the pattern on the top half is the same as on the bottom half, and that's just something interesting to note that will help us later. And this continues. If we look at the start rotation, is sort of split up into these different blocks that are all the same. And then within those blocks, if you look to the right of all these zeros in start rotation, we have sort of 2 blocks of direction and then a bunch of different sort of cycles through of the test number. And the same is true of this block in start rotation with 1s. All of this matches all of this, which matches all of this, and so on. So we've got sort of this recursive pattern where once you've found the right area of the list, the rest of the process is the same, whether you're looking at a start rotation of 0 with the non-I piece or a start rotation of 0 with the I piece. Either way, once you know if you're starting from list item 1 or from list item 40, the process is the same. So let's talk about that in practice. I'm going to write out a little bit of the process for how we want to find the list item, sort of the number that we should look for in the list to get the correct kick coordinates. So the first step is we're just going to start at list item 1. We're always going to start here, right there. Then we're going to say if you have a piece type of I, you need to add 40. And so what this is going to do is say, well, you're going to start at 1 unless you have a piece type of I, in which case you're going to start at 41, right? Because we either do 1 or we add 40 and get 41. And then from there, because we have this symmetry where the entire top half of this list of this organization is the same as the entire bottom half, from here, we can ignore whether or not it's an I piece and just do everything else the same, as long as we start from a different position. All right, let's try the next step. We're going to go to step 3 here. We're going to look at the starting rotation. And we're going to say, add the starting rotation times 10 to your current position. So let's say that we have not an I piece. We'll actually use this example that I already created. We have a T piece, so we're starting at list item 1. That was the first step. Then we do the second step. If it's a piece type of I, it's not. We would add 40. So we don't do anything here. Then we add the starting rotation times 10. Well, if our starting rotation is 1, 1 times 10 is 10. So we're going to say rather than list item 1, we're going to add 10 to this and go to list item 11. And you can see that what we've found so far is the first row that matches both of our 2 criteria, right? We started by finding the first row for piece type of T. That was number 1. And then we added our second criteria, which was the starting rotation. And we found the first row that is a piece type of T, or not I, and a starting rotation of 1. We found this first sort of starting rotation of 1 section. All right, then we want to go to the direction. And we say, well, if you have a direction of 1, if the direction is 1, add 5. And that's because sort of if you have 1, rather than starting at number 11, in order to get down to this row, number 16, which is the correct row because we're not going in direction -1, we're going in direction 1. To get from 11 to 16, we have to add 5. All right, then we want to get to the final step, which is to say, if we have a test number of 3, we have to go down 2 in order to get there. And so the final step of our process is add the test number -1. And that's going to get us the correct list item to look at in order to find the correct kick information that's going to give us the sort of position that we need to move the piece. So all of this is kind of a lot to take in. I would really encourage you to go and open up this spreadsheet and really play around with it for yourself. You can even look at this formula that I've made, and the color coding here might help. You might be able to sort of identify how this formula matches up exactly to the 5 steps that we've created here. Starting at list item 1 is sort of the last step in the formula, but other than that, it all lines up pretty well. And you should be able to sort of see how this works. And I would strongly encourage you to do that, but even if you don't want to, if you're willing to sort of accept that this process works, that it's going to find the right list item for us because of the sort of pattern in the way that these list items are organized, we know that this can be really helpful in our Scratch project. So let's start by taking the X and the Y lists and actually putting them in Scratch. Now, fortunately, there's a pretty good way of doing this. I'm going to have to clear out our helpful little instructions here. But what we do is we can take this entire list of X coordinates, and rather than manually typing them into a Scratch list, we can just import them. So I just pasted this in. This is the entire list of X coordinates, and then we're just going to save it. And I will save it to my desktop. I don't normally do that, but just for being fast for video purposes, and we'll call it kickx.txt. All right. Then we can go back into our Scratch project, and we can make a new list, and I'll call it kickx. It doesn't have to be the same as the name of our file, but they both are sort of talking about the same thing. And then what we can do is we can just right-click on our list and import the file that we just created. And because we have all of these different list items, all on each a different line, we can click the open, and it will just give us, you can see, a length of 80. It gives us all 80 list items right in Scratch. So that's a super helpful tool. And we're going to do the same thing with the Y. So we're going to say, copy all of these Y coordinates for all of our different kicks that we want to try. And I'm going to delete everything here and paste in the Y values. And again, each of them is on their own line. So then we just save it, and we'll save this one as kick Y, and then we can import it into Scratch. So we'll make another list called kick Y for this sprite only, and we'll import our list. All right, so we have these two lists that are our spreadsheet data sort of put into Scratch. And now what we need to do is take that process that we created that allows us to find the kick coordinates and implement it in code. So let's try this out. I'm going to say, this is sort of our rotate action that says when you press the up arrow, do the rotation. And I'm going to turn this into its own custom block just to make things a little bit cleaner. So I'm going to make a block called rotate piece, and then we will have the direction. And this direction will line up with this will sort of be used as column D in our search to find. So this direction that we have in the custom block will either be 1 or -1 for clockwise or counterclockwise, and we'll use that when we're finding the correct list item. So here we are. We're going to rotate a piece at a particular direction, and we will just say now, I've sort of attached our old code into this new custom block, and we will say that when you press the up arrow, you need to rotate the piece in direction 1, clockwise. Okay, so now I got to find a spot for this code here. It might help if I zoom out. We can find a little place for it, maybe down here. All right, perfect. Then we'll zoom way back in. All right, here we are. So we want to rotate the piece, but we want to try sort of 5 different tests, 5 different kicks. And so we'll start by finding the first kick. And we actually know that the first kick to try will always be 0, 0. If I highlight these different rows here, these are all of the sort of test number 1 rows. So you can see if test number is 1, it's always going to be 0, 0, which makes sense because we're always going to start by testing just a rotation with no kick at all. But in order to find the correct list item, we need to take our process that we came up with for getting the list item number, and we need to implement that in code. So if you remember our instructions, which we had to get rid of, unfortunately, in order to save the list and import it into Scratch, we said start at list item number 1. Always start at list item number 1. Then, if the piece type is I, add 40. That was the first step. If the piece type is I, then rather than starting at number 1, we're going to start at 41, which makes sense because this is where all of the I pieces live. So we say if the piece type that we're rotating is an I piece, then we want to change the list item number, and I'm using the variable I for this, change it by 40. So we need to check the piece type, that's this variable here, and if we play around with our piece type variable, remember it's item 1, or piece type number 1 is this I piece, this big long one. So if piece type is 1, if it's the big long I piece, change our list item number by 40. All right, then we've got to look at the starting rotation. Well, every time the starting rotation increases by 1, our list item should increase by 10. So we're going to say change our list item number by 10 multiplied by the, what was it? The piece, I forgot, the starting rotation. So the piece rotation times 10 is going to say every time the piece rotation goes up by 1, make the list item that we start at go up by 10. All right, then we want to focus on the direction. And we say if it's a direction of -1, don't do anything. You're already in the right spot. But if it's a direction of 1, we need to add 5. And remember, the direction here comes from our custom block. This will allow us to use the block to rotate in either direction. If the direction is 1, if we're rotating clockwise, then we need to change our starting list item by 1. All right, then the last step here is the test number. And in our code, we sort of had in our process that we did in the text editor, we sort of write out the instructions. We said add the test number -1. But essentially what we're saying is start at test number 1 by adding 0, by just going where we already are, and then continually add 1 each time the test number goes up, right? So all 5 tests are always going to be in order in our list. Our process that we have so far will already find the first test, and then each one after that is just sort of moving up by 1. And so rather than sort of programming that in, we'll make a repeat loop that's going to repeat 5, and every time that we want to try a new test, we just change our I by 1. And we can do that 5 times, and it'll give us 5 new tests that all have sort of the same conditions, the same piece type, rotation, and direction. So now, inside the top of this repeat loop, we have the test. We have I representing the list item that we should check in order to get the kick coordinates. So we want to actually try doing it. We're going to take this code, and we're going to say it's time to check if the piece is valid when we include the kick. Now, the first thing we want to do is use our direction to say, take the piece rotation, and rather than just adding 1, which is what we were doing before, we used to be adding 1 because we just wanted to always rotate clockwise using the up arrow, and we're still kind of doing that. We're still kind of plugging 1 into this direction, always when we press the up arrow, but we want to actually plug this variable in so that we can try -1 in the future as well. All right, so we're going to use our direction, but then the big key is, for the x and y, we're not necessarily just going to leave the x and y how they are. We're going to actually try doing the kick. So we're going to take the piece x, and we're going to add a little bit of information. We're going to add the kick x. So we're going to try our kick. We're going to find the x. And remember, we want to know which list item, which kick should we try? And the answer is, well, we've stored it in this variable I. That's the whole point of all this script at the top. All right, so that gives us the x with the kick included. Then we want to get the y with the kick included. So rather than piece x, we're going to try piece y. And rather than kick x, we're going to try kick y. And so this will give us sort of the x, y, rotation, and type of the spot that we want to try. And we're going to check if that spot is valid. And if it is, then we want to set the piece rotation, which we've already done, but we also want to set the piece x and y. We want to actually perform the kick, right? If it worked, if it's valid, we should actually do it. So we're going to change the piece x, and we're going to change the piece y in order to actually perform the kick. And again, we can just take this kick information from the list because we know which list item we're supposed to be looking at. All right, so this right here will do almost what we want. There's just one problem, which is that if the kick is valid, if we try a rotation and it works, we want to abort. We want to say, hey, stop doing this repeat 5 loop. We don't need to try the other 5 tests or the other 4 tests. We already found one that works, right? And so we just want to say, abort, abort, stop this loop. But Scratch doesn't really give us a super easy way to do this. And so what I'm going to do is I'm going to use this, I think we'll use, let's see. Actually, here's a good way of doing it. We will say, in the beginning, set is valid to false. We'll say we haven't found a valid rotation yet. We haven't found a valid rotation with a kick that works. But then when we do the check if piece type is valid, remember that sets our is valid variable. And so what we'll do is every time we go through the loop, we're only going to run the new kick if we haven't found a good one yet, if is valid is false, right? So we're going to say in the beginning, yeah, is valid is false because we haven't found a good working kick yet. But then every time we go through the loop, every time we try a new test, we're only going to actually try it if is valid is still false, if we haven't found a good kick that works yet. If we do, if is valid becomes true, then we'll actually apply the rotation, and the rest of the times that we go through this loop, nothing will happen. All right, let's try this out. This was a lot of code and a lot of talking, but the hope is that now it will work. So it looks like my rotation here, I think, is still working. Although, it looks like my piece X is changing a little bit. See, when I rotate, the X is changing even though it shouldn't be. Right now, no real kick should be happening. It should always be trying that 0-0 kick. You can see even this piece moves when I rotate it. So I'll have to do a little bit of investigative work here and see if we can figure out exactly what's going wrong. Alright, I've taken longer than I care to admit searching for this bug, and it turns out it was pretty straightforward, and probably all of you in the comments were screaming at me. I'm sure you all saw it faster than I did. In this direction check, where we're saying if direction equals 1, we have a change I by 1 here. But when we go to our list, if our direction is 1, we should jump forward 5. For example, going from list item 1 to list item 6 to get from direction is -1 to direction equals 1. So this change I by 1 needs to be a change I by 5. And that way we'll get the right list item. So the reason it was moving back and forth is just because we were finding the wrong kick X and kick Y. All right, let's try this again. Ooh, we have an I piece here, which is perhaps the most interesting. It looks like it's working, but let's try moving it over to the side. And oh yes, you can see that it's kicking. It's ending up in a different spot than it started. Let's try it again. If I rotate this, it wouldn't work before, but now you can see it kicked to the right. I did full 4 rotations, and without pressing the right or left arrow keys, I ended up shifted 1 to the right. Same thing here. I rotated 4 times, and I ended up shifted 1 to the right. These kicks are working. I can try it on the right as well. Normally, I wouldn't be able to rotate here, but it will kick me out 1, and now I end up in a slightly different position. So where I couldn't rotate before, now I can. I can press the up arrow, and it will find a nearby position that works in order to allow me to rotate the piece. So this was a lot of effort. It was kind of a big day. We've got a big spreadsheet of sort of numbers to wrap our mind around, and I would still strongly encourage you, especially if you feel like you don't fully understand this process. I wish that I had a clearer way to explain it. I really do. And maybe someone in the comments has sort of a clear explanation. I think that would be awesome. It's something that I've sort of had a hard time articulating, but essentially, we've taken this data that's very difficult to represent with if statements or logic, and instead of trying to write code that figures out what the values are, we try to write code that figures out where the values are. And if we can just arrange them in sort of an intelligent way, we can make our lives a lot easier. So I would strongly encourage you to check out this spreadsheet for yourself, play around with this little formula that finds and highlights the correct list item. Play around with this, see if it makes sense to you, and I would really sort of strongly encourage you to take a look and maybe try to explain it to each other. I do feel a little bit bad. I feel like I didn't do a proper job of really articulating exactly how this works, but I'm hoping that it came across clear enough, and maybe you all can help each other understand a little bit as well. If you have specific questions, I can try to answer them. That might clear things up. And maybe I'm off base here. Maybe it actually did totally land and make sense, and I hope that's the case. But we've got these wall kicks working, and in the next video, we'll try something a little bit simpler and a little bit maybe more fun to spice up our game and put some finishing touches on it.